Değerli hocalarım, değerli gençler, hepiniz hoş geldiniz. Bugün 3D baskıya giriş ve topoloji optimizasyonu konusunda Almanya Hamburg'dan, Heinkel gruptan Tayfun Süle hocamız sizlere bir kısa bir sunum yapacak. Kendisini sahneye davet ediyorum. Buyurun hocam.
Tamam. Bir mikrofon var. Teşekkürler. Memnun oldum burası size önünde bir şeyler göstermeye. İlk önce diyeyim, ben Almanya'da doğmuşum. Benim Türkçem o kadar fazla iyi değil. Çoğu şeyde İngilizce diyeceğim. Sorular tabii Türkçe sorabilirsiniz. Her an diyebilirsiniz. O zaman ben başlayayım o zaman. Takıldı buraya. I'm born and raised in Germany, in the north of Germany, and living in Hamburg. And since 2011, I'm working for the Heinkel Group in Hamburg. I studied aircraft engineering. It's called Uzay and Uçak faculty in the ETU. And after that, I'm doing my master's thesis in composites. And since 2011, I'm also working for the Heinkel Group. And since 2014, I'm the responsible for all additive manufacturing activities at our company. And our company himself, we are existing since 1974. Airbus is one of our main customers, so we're doing a lot in the aerospace field. And we are around 120 employees from all over the world. So we have a lot of Turkish people, we have a lot of Spanish people and Italian people. And so in total it's about 20 nations. Our headquarters is also in Hamburg based, but we are also on other locations in Germany. To show you a bit better, the difference between the Heinkel Group and the Bionic Studio. The Heinkel Group is split in 3 parts. We have the Heinkel experts, where we send our employees to companies like Airbus and they work for them. We have the HR services, so if big companies are searching for new employees, they're asking us and we're doing the recruitment for them. And where I'm working is the engineering team. And into this engineering team, we created the Bionic Studio. The Bionic Studio is especially for additive manufacturing activities to have a bit more focus on this theme. It's because we are not just doing 3D printing, we are also doing other stuff like stress engineering, cabin engineering in the aerospace field, acoustics, scientific programming, 3D printing, and steel construction. In my team, we are around 17 people for additive manufacturing activities, and we're working in different branches like the aerospace, automotive, mechanical engineering, steel, and also fashion and food. It's also quite interesting. Does any one of you has already contact with 3D printing? 3D baskıdan bir şey yapan birileri var mı? Siz yaptınız. And for the rest, it's a quite new stuff, as I understand, right? Okay. I will give you a short introduction to how 3D printing works, and one last slide before that. So our services are split in 4 main parts. So we have the consulting, where we're searching for parts which are interesting for 3D printing, because not every part can be 3D printed, and it sometimes makes no sense to print it in 3D. We're doing workshops and education stuff. We have the development for design, construction, and so on. And I will show you already one part, and I will show it later in more detail. This is a part out of the A380. Airbus A380. Normally it's like this. It's broken in my baggage, so sorry for that. And I will give it around. It's out of plastic. The original one is in aluminum. And I will give you more details later, but you can give it around for us. So what is 3D printing? So in the end, it's not that complex. You're laying thin layers in two-dimensional way and build a part up. So you can construct a part by doing this. And to show you this, I have a little video which is showing. It's very slow, just to show how it works. So you have a hot nozzle where you put plastic through it. Does someone of you ever used a hot glue pistol? Yeah, you use it. So it's nothing complicated. You have this nozzle, you heat up the material, you can lay it down, you let it cool it down and lay another layer on it. So, and if you do this layer by layer, you have a wall. In this case, I think it's a part of a tire, and you put material on the places where you need it. So you have the subtractive manufacturing, where you do milling and drilling or whatever, and you have the additive manufacturing where you put the material on the place where you need it. And this is one of the techniques. It's called FDM, fused deposit molding. There are a lot more. Another one is the selective laser melting. Yeah, wait a second. In this case, you have metal powder or plastic powder, and you're shooting with a laser on the places where you want that the metal should be melted. And you're doing this also layer by layer, and building the parts up then. Yeah. And materials is quite interesting because you can already print a lot of materials. So you can print all weldable materials like steel, aluminum, titanium, or gold. Titanium is quite interesting. It's also already certified for the aerospace field. So Airbus is printing a lot with titanium, and aluminum is coming also a lot. You can print a lot of types of plastics, so like ABS or PLA. ABS is the plastic which you have on your car, for example. This is used a lot there. You can print ceramics, so the dental branch, the dental industries are already doing a lot with 3D printing to print teeth and so on. You can print organics stuff, so and also food or glass. Food could be interesting for the old people who don't have teeth and can't chew and so on, to create the possibility to eat something. Historical. The 3D printing is developed in 1983 by this guy, Chuck Hall, and his idea was to rapid prototyping parts, to have it quite fast. And in the last years, we had a hype. So everyone is speaking about 3D printing because it's quite interesting, but the technology himself is around 30 years old. Does someone of you have an idea why this happened now, why we have now this hype and not 30 years before? Someone has an idea?
Computer power.
Huh?
Computer power.
Yeah, computer power could be. Oh. Computer power could be. But you see the first patents are from 1986, and the most patents are lasting 30 years roundabout. So the patents are going over right now, and more companies are trying to use this technology. And this is maybe one of the main reasons. Should we do a little break or something? As I started 4 years before with 3D printing, we was sitting down with our colleagues and was thinking about, so for which industry it could be interesting to print something in 3D. And we're sitting there for 1 hour with 5 people and had so much ideas, and in the end we changed this. We do it a completely different way. We think about branches or industries where it's not interesting to print 3D because it's regarding a lot. And if you start, sorry for this slide, it's in German. If you start here on the top, you have the parts for the airplane. Especially if you need just small batches, small lot sizes, just a few parts and not thousands of parts like in automotive, it's getting interesting because you don't need to create molds and milling and frequencies and so on. And you have, for example, this prototyping in the machine industry. This is something interesting for you. You have also implants or prostheses, and Adidas and Nike, they have already started to print shoes where they scan your foot and you have foot, and 20 minutes later you have a sole and they can create a whole shoe around it. There's also art stuff, toys and fashion and whatever. So, and in different ways. And where we start with it, maybe some of you saw this part here. It's the first printed part out of titanium, and it's flying in the A350, Airbus A350. It's on the galley, so and it ensures that if the plane crashes to a wall, that the galley is not falling down to the passengers in front. So it has very high loads on it, and it is around about 20 kilonewtons, and it is just 120 grams. So it's not really heavy, but it's holding a lot. It has to do with these bionic structures on it. And this was the first project where we do the calculations of the, or do analysis of the part himself. And you see here another part. This is the bionic partition. This is done with the company Autodesk together, and it's a wall which is quite high. It's around 2 meters, and it's printed in parts. And you see here the parts, and they will connect it after the print. And yeah, some advantages here is we have the manufacturing of small batches. We can lose the weight. So, for example, in this case, it's around 30%. In this case, around 40–50% of weight loss. We can manufacture faster, more complex parts, because if you think to produce something like this, you will never finish it, or it will be really expensive. You can integrate new functions, so it's no matter if you put a hoe or something in it, and you can guide hydraulics or electronic cables inside, and so you can integrate these functions. You can simplify the design, and yeah, generally you can design stuff which is not possible on a conventional way. But there are also some disadvantages. So this technology is really slow. To print something like the part which is going around, it takes on a normal FDM printer around 2, 3, 4 days. It depends on how good the quality should be. And the second thing is the automatization. So you see the guy who's there with a sucker and sucks the powder out and having a mask on it, and it takes time. So it's not a really automized project. Most companies are trying to automatize it more and more, but it's not like a milling machine which is finished and there's a KUKA robota which is touching this part and bringing it into the next. So this is not working right now for this 3D printing. And the quality, and if you see the part, I mean, this is a cheap printer. It's an FDM printer what we use, but it has not a good surface quality, and it has not the stability, and of course also the reliability. So it's not that you're starting one print in 2 different machines and you're getting the same results. You have a high invest, so these machines you have to think about 500,000 euros and more for it, and the know-how. So the first thing what I have done before we start with 3D printing in our company, I just ordered 3 3D printers and tell our employees, so please, you can use it for whatever you want. So you can use it for home use, you can use it for work-related stuff, whatever. And it was not that they starting with it and they directly get a part out of it. So it's really, you need a lot of know-how to understand how this stuff works, and how you get parts in a good quality and in a good time out of it. So especially for metal machines, most companies are saying you need 1.5 years to understand the technology before you can sell the products out of them. And the certification. So in the aerospace field, it's quite interesting to have a certified part. So you need a certified material, you need a certified machine, and a certified process. And all the stuff is not done right now. It's not that you're buying a book and taking a look at it and know how the drilling speed should be and how the milling speed should be and whatever. This is quite experimental right now. The question is now, why are we doing it? And some of the advantages I already told. So the one thing is you can produce data out of the CAD work, what you have done. It's not that you have to switch it to a CAM language to feed a milling machine or whatever. So you can directly use your CAD files, put it in a 3D printer, and can print it. In small batches, I already told, reducing of the development time. So you can produce different types of product in a very short time and test it before you're going to do it bigger. So you can reduce with this your development time. You don't need tools. So if you want to produce a plastic mold or something, you need time and money for it, and this 3D printer don't need molds or tools for the reasons. And one of the main things is you have the geometrical freedom. So you can decrease the weight, you can increase the functions, you can build up complex structures, and you can substitute parts. And this is the reason why I show this part, which is going around right now. These are 5 parts, and you are able to substitute. Some people ask me a lot if the 3D printing machines will substitute the milling machines or the drilling machines and so on. My feeling is that it will never substitute some other technique. It's just a new way to produce something. And let me show you this. So if you have the conventional manufacturing with milling, for example, if you produce a plate, it's really easy. So it's not that complex, and the price is also not so high. But if you want to produce something really complicated, the price is going higher and higher. For additive manufacturing, it's nearly no difference. So the 3D printer doesn't matter how complex the part is. So you have also always to think about on which way you are, and you have to compare: is it better to print it, or is it better to mill it? And at this point where both lines are crossing, you're starting with we call it complexity for free. So from this point on, it doesn't matter how complex your part is going to be. You can print it because it's mostly cheaper than to create the conventional manufacturing way. And let's come to this part. I will show you one example. The most examples I cannot show to you because we are just an engineering company, and customers come to us and ask us to help solve their problems. So we don't have own products. So this is something out of a bachelor thesis. And this part is hanging in the A380. It's on the top, and it's holding the oxygen boxes, which you have over your head. And it's 5 parts. 2 of them are milled parts. 3 of them are sheet metal parts. And it has 17 connecting devices, like rivets or nuts and so on. And the total weight is 239 grams, originally from aluminium. And maybe just to keep it in mind, the price of this part is around, as in complete, around 60 euros. So just for the parts themselves. And what we do first is we do a topology optimization. Does someone of you, I think you had already contact with topology optimization a bit. Does somebody of you heard topology optimization? You also? Okay, a few of them. I will show you later a few examples on it. So what we do in topology optimization. So I will go one back. So we have this part which is really complicated. It is connected here and it has connections here and so on. And what we're doing first is to create a design space. We will do it later on an example. So we create this design space. This is this grey area. And the yellow areas are areas where we're saying to the program that these areas can't be changed because there's a force on it, there's a connection on it, and it must be stay for quality reasons or whatever. And this program is doing one thing. It's thinking about how the forces can flow through the model to the points where it's needed. And there's mostly coming out something like this. This is what the topology optimization gives us as a result. And from this one, we can start to create a CAD model. And this can look like this. I have it here with me. It's an aluminum part. I will give it also around. So what we have done is we substitute 5 parts to 1. So we have just 1 part, and it's just 53 grams. In this case, we save nearly 80% of weight. We save the parts 80% and the connecting devices, so we have less connections. And but this part is the cost of this part is around 120 euros. So it's the double of the other parts. What you keep in mind then is there's no guy who's sitting there and assemble all the parts together. There's no one who's trying to take the tolerances and check if everything has the right tolerance and so on. You have less logistics, so you don't need to order 5 parts. You just have to order 1 part. So if you keep this stuff in mind, it can be that this part is more cheaper than the old one. So this is the reason why it could be very interesting. And yeah, let me think about it. Then let's come to the point where we have a little example. The following thing So the flight from Hamburg to Istanbul is about 3 hours. And the following thing I have done in the plane, I was thinking about a wardrobe hook, so where you put your jacket on. And I designed this wardrobe hook, and I was thinking about, okay, it has 2 connections. We have here a force about around 100 newtons, and we have a weight of 200 something gram. And I will split now to Autodesk. Just a second. Someone of you already used Autodesk Fusion 360? You used it? Someone of you know Autodesk Fusion 360? A few more. Okay, it's a quite interesting tool because you have different stuff you can do. I'm sorry because my version is in German, but I will try to explain it. So we have the model component where you can design something. You can design shapes. This doesn't matter for now. You can render stuff. You can animate stuff. So how an explosion view or something or whatever. And then you have a simulation, and this is quite interesting because the most tools like, for example, CATIA don't have everything inside. What kind of software are you using for design or analysis? Can someone told me was something? SolidWorks. Tinkercad. CATIA maybe also, or Siemens, maybe Siemens NX. Okay. The good thing with Autodesk is you can have everything together in one program, because previously we had it that we have to design something with CATIA, then export it, put it in Patra Nastran to calculate it, then put it back in Siemens NX for the final designs, and it always depends on our customers. We have different customers and different branches, and the one company is saying, oh, you have to do it in Abacus, the calculation, and the design must be in CATIA, and it's so different. And so we are always asked to do it. And what I like to do from scratch now is to create this wardrobe hook. It's quite easy. So we have this sketch tool, choose a plane. I have to say something more in front. So I have done it in 3 hours on a plane, but I'm using it since half a year, and I've never get a workshop or something on it. Everything what I know I've done by my own. So it is maybe showing how easy this program works. So what I do here now is to create this wardrobe hook. Zack. Maybe a bit too much. So, and it's maybe not. And then we need 2 holes here. It's not symmetrical, sorry for that, but it's just to show you quite fast how it works. No. So, finished. Who was it who used CATIA? You use CATIA. How long do you need to do this? Same operations? 3 minutes, okay. I've done it in 40 seconds. So, does he agree? So, and it's a really easy part. So it changed a bit the way of designing something. So it's not that complex like other programs. And this is quite interesting for us because our engineers are mainly calculating something, doing CAE analysis and FEM analysis and so on. And they don't have an idea how CAD works. And what we have done in our office is, so we have the one side of the office which is doing design and the other side of the office who's doing the calculations. And previously it was that the designers design something, give it to the calculators, I would say, and they say, oh, it's completely shit what you have done, and give it back to the designers. And then we have these loops, and sometimes 3, 4, 5 loops, and they don't really speak with each other. And what we have done now is to give them Autodesk Fusion and just tell them, okay, it's quite easy, put your design on it, do a little calculation so you have a first idea how it works. And this is working quite well, and we're turning less loops then. And I will go back to the presentation. And the next step would be to analyze this part, and to have it in line. I will open the next version. So we have here this original. So why we analyze this original part? We like to compare it later with the 3D printed part. So here's the part again. To analyze something, we can go to simulation, and you have now different types of simulation. You can do terminal analysis. You can calculate the frequencies or nonlinear stuff, and also topology optimization, or you can do the normal static analysis. And this is what we would like to do now. In this case, we're starting from the left. So first we have the material. There are a lot of different materials inside. You can change it to other materials. You can create own materials. I will leave it like it is. Then we have the boundary conditions. So in the end, we have here the both rivets. We can just use it to create boundary conditions. And in this case, it's fixed in all directions. So in UX, we have UI and UZ. There are also possibilities to create boundaries which are sliding or fixed in a degree of angle, and then we have a force here. It's the next one. So we just can choose this one, and we say this is 100 newtons, and I will change it a bit. So 5 degrees in this direction, 5 degrees in this direction, because you never pull on a hook really straight in one direction. So. And if you have this, right now we have more parts. I will show it to you. So this is the body. So we have the hook here in the front. You have the hole 1, hole 2, and this is the topology optimized area. And we're doing this context simulation. So it is automatically creating a mesh between the parts. And then you can go to the results, and it's also quite interesting. You can do the analysis in the cloud, where are really big computers which are controlling. I think it's Amazon services or something. So you have a lot of power on it, especially if you have big calculation. In this case, I will do a local analysis because it's, for this case it's totally enough. And you say that this is doing, and now he's preparing the model. Now he's creating the context. Now he's doing the mesh. And if this is finished, he's starting with the analysis himself. And normally it should just take a few moments. So now we have the results. And now we can check the model. So we can go to stresses and see that we have the most stresses here in this area. It's with 22 megapascals. You can see the deformation. So we have 0.33 millimeters of deformation displacements. And some other stuff also. So, but this is first enough for the first analysis. So, and this is what I also already write here down. So we have 24 millimeters of stress and the displacement of 0.32 millimeters. If you like to do a topology optimization right now, we need to know that we are able to find a way how the force is going from the attachments to the point of the introduction of the force. And usually you have more space which you can use for the design space. So like for this bracket, what you see before. In this area, for example, are some cables where you cannot create a design space, but in this area you have a lot of space where you can change something. And to do this, just a second. For example, I was just thinking about something like this. So we can just extend this surface. By creating so now we have a bigger area. And second, So, and for the topology optimization, it's the same like for the analyzer himself. So we have to create the boundary conditions first. We go to simulation again. In this case, we'll do a new study and say topology optimization, and we're starting from scratch again. So we have the materials, I'll leave it like it is. We have the boundary conditions. It's the same like for the other one. And we have the force here in the front. Again, 5 degrees. Okay. So, this is already created. This is the force. And we always need, maybe you ask yourself why I've splitted the holes. There it is. So I split the holes in two parts. So we have this one part and this one part. The reason is, if you like to do a topology optimization, he's going through the whole part, which you say that this is the goal. And to set up the goals, or to say the program what he should optimize and what not, we have to give him a goal. So we're saying that this part can be optimized, the other part should stay like it is. And if you choose this one, you're quite finished, and now you can choose to calculate it. In this case, it must be in the cloud because it's a really high and complex calculation, which is running in the background. And I've already done it, but before we do it, just a second. I'd like to show you something about topology optimization. I think every one of you have a smartphone. Do you know this app TopOpt? No? If you like, you can just download it. It's for free, and it's quite easy, and it's not so big, so you can do it very fast. And we will do a little example by your own, and we'll see if everyone of you can imagine what it brings. So topology optimization, it's if you see it like this, it's quite easy. So there are different methods of topology optimization. If you have a box full of little squares, and you're giving force to the one side, and maybe some of you already see results from an FEM analysis, where you have blue areas and red areas. So the red areas are critical areas, the blue areas doesn't have force on it. And this method for topology optimization, it's called the SIMP method. It's trying to find the areas where no forces are attached and give the expression in densities. And it's doing it in very few steps to create a part which is just withstanding the loads on this point. Does someone of you already downloaded it? Yeah? No? Okay. If yes, this is the optimization task. So it's quite easy. I think every one of you have done it already. So we have a fixed point here. We have a point which can be movable on here, and we have a force attached to this point. And what do you think? What could also you can now you have this whole box where this app can optimize and give a structure. What do you think? How the structure could be? Where do you have this problem? Where you have a fixation here and have a force in the middle, or it must be not just a force; it can be also pressure on the overside. Especially in Istanbul, maybe you drive a lot over it. Bridge, yes, it's a bridge. And if you run this problem with this program, it will automatically give you something like this. And this is quite looked as a bridge. And topology optimization is also nothing new. They use it since years, but now it's possible to create parts which are really complex with a 3D printer. And there are already some companies which are trying to build bridges with 3D printers. It's quite interesting to see, but this is a bit too big for this, I think. And you can play around later. I will give it a presentation. So, and let's assume that the boundary conditions. So after you created this topology optimization, you will get something which looks like this. So in the end, so we have this whole area where this topology optimization can create something, and in the end it says we don't need material on this corner, we don't need material on this corner, we don't need material inside. And if you turn it a bit, you can also see there's also nothing much in this area. And also the connection to the hook himself could be much more or less. And what you also see is there's no material connected to the upper hole. And this is an indice for it that it maybe doesn't need it anymore. So this is also what we see a lot, that for some parts there are a lot of connecting devices to the frame or whatever, and mostly you don't need it. It's just because someone is saying maybe it could be needed. But in the topology optimization, you can see it quite good at this point. And what we do then is to bring it into the design, and we can leave it like it is now, but it doesn't look really well. So if you give something like this to your customer, you will say, okay, nice, but it looks really terrible. So it has holes inside, and it's not straight, and our customers won't like it. So you have to create a good design then. And to take a look at it here. And one of the main things is to understand the design. So what we're doing a lot is we're thinking about on a natural way. So we're thinking about how the nature is doing it. So we're transmitting force, for example. We're transmitting heat. We're transmitting turning devices and so on. And we have to think about how the nature is doing it. There's a quite good homepage. I don't know, maybe if you know it, it's asknature.org. And there you can type in your problem. For example, you have a transmitting between 2 points, and this website is showing you how the nature is doing it. And we're thinking about bionic structures or biomimetic structures, and try to find something which is fitting to this problem. And you was the guy with CATIA, right? If you'd like to design something like this, you will need a whole day, right?
I don't know optimization, and I don't know any theory.
Yeah, I mean, if you have to design or to do with CATIA something like this, no optimization. It's just to design something which is looking like this. You will not do it in 3 minutes, right?
I will design like that.
Okay, yeah, because it's, for CATIA, it's you need quite a bit of time to do this. In Autodesk, I will just show you very fast how it works in Autodesk. So you can just create a plane. Just a second. So now we have this first stuff, and then we can go through it and create. It doesn't look really good, but I have a prepared version. So, and you can go on like this, and I will open the prepared version. This is what I have done in the plane. This is what I have done in the plane. It looks like this. So it's empty here. It has this connecting here, and does any one of you already created a CAM routine to mill something? Maybe not. Not okay. It's quite interesting because when you think about how to produce it in a conventional way, so there's no way to go inside this part and mill something out here, and also this area. So it's not really easy to do. And here I have it. So we have the same steps. So it's in this case we just have one attachment instead of two. We have again 100 newtons and a weight from just 77 grams. Things. And what we have done, what we have to do then is to analyze it again. And I already prepared it here, simulation. So we have here the analysis. In this case, we can see we have now a bit more of stress at this point, but it doesn't matter because the material is for around 270 megapascals, so it doesn't matter in this case. And we have a displacement of 0.1. And if we compare this to each other, so we by doing a topology optimization on this just one part, we saved around 65% of weight. The connecting device is just the half, and the max stress it's a bit more higher, but doesn't matter for this part. But the most interesting thing, we get material out from the part and increase the stiffness. So the deformation is minus 68%. Before it was 0.33 millimeters. Now we just have 0.1 millimeter. So by taking out forces and thinking about bionic structures, we could improve the deformation at this point, so it doesn't move that much like before. And one of the last things I'd like to show you is the rendering. This is quite interesting with Autodesk. So you have this tool. You can go to rendering. And it's always good if you have good customers, if you render the pictures before, because it looks more realistic, and it's quite easy. You can render it with a quite tool, or you can go through this point where it's starting to render pictures, and you can choose the different types of materials. So right now it's metal, but you can also choose leather, for example, or I will take water, because it looks always interesting. Yeah, it takes a bit, but then he starts to render the stuff, and you have cool pictures from it. And also, if you have assemblies, you can create an exploded view where you can where you can see all your parts which are getting inside. And I will leave it run because I'm more or less this at the end. So this is, for example, it's a red glass, and that's it. And I'm open for a discussion or questions, and hopefully it was not too fast and understandable. You can ask your questions in Turkish if you want. I will understand it. I'm trying to answer it also in Turkish. Yeah? Okay. Any questions already?
So what was the reason for...
You will get a microphone.
So in your topology optimization design, you have the angled empty slices, right?
Yeah.
So why are they angled instead of straight?
I mean, I've done it in a plane, and I was thinking that straight lines are looking quite easy. This is more or less a crazy idea of myself. So, but of course, I could also choose another angle, so in another way. So, but in this case, it's counterproductive for the stiffness. If you do it to the left, it will increase the stiffness a bit in this point. But I'm not sure if there's an example from the nature. So it was just a really sharp idea for me. Yeah.
And the question is the ceramics you mentioned about the ceramics additive manufacturing. So. Do you have concrete examples that they are using in, for example, dental industry?
Yeah.
That rely on ceramic parts made out of additive manufacturing?
Mm-hmm. So in the dental branch, they're using a lot to create teeth of it. There are also companies which are creating. I don't know the English name for it. It's this plates for milling and drilling machines where you have really high forces on it and where you have really high temperatures on it, and they're using it also in this area because normally you can't really create ceramics or this high temperature metals without destroying other stuff, and in this case you can create this ceramics to do it in an easier way.
Do they use SLM or binder jetting?
It's mostly in SLM. I heard also about binder jet where you have to put it in an oven later to reduce the binding material. Yeah. Okay. And maybe we can switch the microphone.
So thanks for coming. My question is about Fusion 360.
Mm-hmm.
In the analysis part, is there a way for you to see the mesh of the?
Yeah, of course. Okay.
solution?
I can show it very quick. So let me switch to this or not this one. And you can also modify the mesh at this point. So
Yeah, because the refinement of the mesh is important in here.
Mhm.
And
oh, so this was the wrong one. Just a second.
is the program allows us to refine the mesh with some tools?
Yeah, I will show it to you just if I find it. So here you have the mesh now, and you are able to this. How was it? You can refine it here with this one, or you can say an absolute thickness of the mesh, and you can say you have much more parametric stuff where you can choose that in corners he should create more mesh size. You can. There's also a tool. I'm not able how to find it right now. Where you can click on specific areas to change the mesh at this point. It's quite good. So we have done some tests with against Patran, Nastran. It's another FEM program what we use a lot, and it looks more or less the same. So I mean it's not.
Actually, the underlying engine is Nastran.
Yeah, yeah. This is maybe a good point. So in the background, the calculation itself is created by Ms. Nastran. You're welcome. We have something in the front.
Thanks for your presentation.
Welcome.
We access the boundary condition. So what about the design limitation, the manufacturing limitations? If I want to manufacture with the injection molding, how can I access the design and manufacturing limitations?
I'm not so sure about the limitations for injection molding. I think this is not really.
For 3D printing, or
I have the knowledge in 3D printing, so that's the reason. You have here this CAM part where you can create stuff for multi-axial milling machines and drilling machines, but as I know, there's nothing to build molds or something for plastic injection. Am I right?
There's no plastic injection module within Fusion.
Yep.
It's about CNC
Yep.
and 3D.
Yeah. Other questions? And Türkçe sorabilirsiniz yani.
Aslında epey bir vaktimiz var. Yani şu
Hı?
anda bir örnek daha yapmak ister misiniz bu topoloji optimizasyonu ile ilgili? Mesela bilmiyorum, dolaştırdığınız parçaları çok mu karmaşık olur? Ya da o
İstersen birkaç şeyler gösterebilirim. Bizim yaptığımız birkaç şeyler gösterebilirim. Şimdi with Autodesk Fusion, you are using completely in the cloud, so you can. This is maybe also quite interesting. You have some different projects. For example, this is a child seat for the airplane. So if you have, I think that no one of you have already childs. Me neither. But if you travel with a child in the plane, it's quite not that easy because you have to fix the child during the start and the landing, and you have to put it then in front of yourself. And I don't know if you ever have a baby or something in your front. It's they are getting really hot, especially if you fly in something somewhere which is also, just a second, where is it? And what we think about, this is a project what we have done with another company together, and what we have done there is this is a partition of a plane, and we think about to create something like this, which is foldable, and where you can put your child during the start and the landing, and you're just folding it back and putting it up after the start and the landing. And the good thing with Autodesk is you can collaborate with others together. So in this project, there were different people working on it, and in this case, it's 3, and everyone can create a part of it, and so you're working together. And if you have an assembly, you can assemble everything together, and if someone is changing a part, this will automatically also change. Or if you have someone who's the expert in calculation, he can do the calculations, and you are doing the design, and you can split the work much easier, and it doesn't matter where you sit. So if, for example, if someone of you like to write or to have a project with us in Hamburg, it's no problem to share the data and work with Autodesk Fusion via the internet and the cloud. And this is one example, maybe what's interesting to show you. Every year we're doing a competition on the university where we have a part like this here. So this was the last competition. It's a lever arm from the aircraft, and it has 2 fixation points at this point, and we have a force attached on this point. And what the students had the task of the competition was to optimize this part and to decrease the weight and holding the stability of this part. And for example, the students all work with Autodesk in this case, and these are the results. And every team had the chance to ask us for questions, and we just split this folder together, so we was able to answer these questions. And here you can see the parts now. So it was quite interesting because the team here on the bottom line, it was mechanical engineers from the architecture branch, and they was thinking about I didn't know the English name for it. In German, it's Fachwerk. So they're thinking about the structures like from the bridges where you have this inside here. So, so this is their design. And this team, this was aerospace engineers, and they were thinking about birds, how the birds fly and how the forces can be transmitted. And the last team, this one, this is a bamboo structure, and if you look here inside, you can see here there are some stiffness inside, and so like the bamboo rod, where you have the stiffness inside the rod. And the winner was this one, because this one deforms too much, but it was quite interesting to see the different results of different teams in this case. And yeah, and I can show you the last thing. Just a second. I don't know where it is. There it is. For example, this here is the outcome of the topology optimization of this 1 year. And yeah, this was the first results, and then we created this design for this one. And I will ask you again, can you build this up in CATIA?
Maybe 3 days.
3 days? Yeah. What the other things? How long will it take to create something like this? Also 3 days? Soldex is 3 days. It was quite interesting because our students do it first in CATIA, and he was sitting there for 3 weeks. So now you see the result. Now you see the results, and you can build it up. Maybe it goes faster, but he's sitting there 3 weeks to create this part. And as he created this part, I told him, "Oh, there's a cool new tool. Maybe it could be interesting to create this, and with this other tool, maybe it will be faster." So I recommend him Autodesk Fusion in this case, and I said, "No, I just sit there 3 weeks, and I will not change anything on this part again because it crashes a lot, and especially if you have areas like this where a lot of rods coming together to one part, it takes a lot of time." And in the end, he had before he finished his thesis, he had a bit of time, and I asked him again, "So please try it. I will just like to compare it. So how long will it take?" And in the end, it needs about 1 day for this with Autodesk Fusion. And the interesting stuff was it was more smoother. So here are a lot of corners inside where he don't want to touch it anymore because the model was crashing a lot. And in the end, he got a smoother model, and had done it in 1 day instead of 3 weeks. So. Of course, it's a student, so if you have a full-time worker with CATIA, maybe you can do it faster in 3 days or even faster. But it was interesting to see how, and he never worked with Autodesk Fusion before, so he just started and do it in around 1 day. So just to give an example, how easy it is to understand and use it. And myself, I took a lot looks at YouTube videos how to create and do something. It's quite easy. So I can recommend just try it. It's free for students, I think, right?
Yeah, sure.
Maybe you can tell a few words.
Okay.
Yeah. The microphone is here.
Thank you again, first of all.
Yeah.
It was great. Türkçe, I can switch to Turkish.
Yeah, of course, please.
Sadece Fusion değil tabii. Autodesk'in bütün ürünleri bildiğiniz gibi. Bütün öğrenciler, öğretmenler, okullar için tamamen ücretsiz ve istediğiniz gibi kullanabiliyorsunuz. Laboratuvarlar için de aynı şekilde. Fusion'un bu kadar fark yaratmasının sebebi çok kısa bir ileriye dönük olması, yeni teknoloji olması, bulut tabanlı, kolay öğrenilen, kolay kullanılan ve Tayfun Bey'le biz daha yeni tanıştık. Yani Autodesk'te de hiçbir bağlantısı yok. Kendisi doğrudan endüstride bu işleri kullanan, bu konuda uzmanlaşmış bir insan ve ne sunacağını ben de bilmiyordum. Yani açıkçası daha önce sunumunuzu görmemiştik. Ve bu şekilde çok net bazı şeyler ortaya koymanız, yani bazı doneler ortaya koymanız gerçekten güzel oldu. Umarım faydalanmışsınızdır. Topoloji optimizasyonunun daha ötesinde generative design dediğimiz, generative tasarım konusu geliyor biliyorsunuz. Orada artık algoritmalar, yazılımlar kendi başlarına verdiğiniz constraint'lere göre, verdiğiniz sınırlamalara göre geometriyi kendileri oluşturuyorlar. Yani yapay zekanın devreye girdiği bir dünyadan bahsediyoruz. Onunla ilgili de teknolojilerimiz var. Umuyorum ki daha sizle de birlikte öyle ilgili bir şey yapabiliriz. Daha sonra başka seminerlerde işte generative design konusunda, ileri imalat teknikleri konusunda seminerler yapmaya devam edeceğiz. Çok teşekkür ediyorum. Başka sorularınız varsa yine tabii devam edebilirsiniz.
Okay. Şu arkada bir soru var. İki saniye şunu vereyim size de.
Taahhüt ediyor. Sen bu malzemeyi kullanırsan bu şartlarda başın ağrımaz. Biz böyle bir ürün ürettik diyelim. Yani çıkan ürüne verilen bir garanti var mı? Bu çalışma şartında senin başın hiçbir şekilde ağrımaz. Şimdi burada bir kaynak olayı var baktığımız zaman aslında. Bir şeyin üstüne bir şey ekliyorsunuz, eritip kaynatıyorsunuz.
Evet.
Alüminyumun kaynak problemleri var.
Evet.
Soğuma problemleri var.
Hı-hı.
Sizin yaptığınız ürünü ben elimle böyle biraz sıkıştırdım.
Hı-hı.
Bayağı mukavemet bir şey yani.
Hı-hı.
Ama bu
İyi kırmadınız. Şaka diyorum işte.
Garantisi var mı yani? Kesit sürekli böyle değişen bir geometri var. Bazı yerlerde kesit kalınlaşıyor, bazı yerlerde inceliyor, soğuma karakteri değişiyor. Yani
evet.
Geometriyi kontrol edemezsiniz bu üretim aşamasında. Şimdi oldu ki biz çok hayati bir şey yaptık böyle. Koyduk onu oraya, biz bunu editimle yaptık ama kırıldı.
Hı-hı.
Başımız ağrıdı, bizi mahkemeye verdiler.
Evet.
Biz buna güvenerek bu şirketin ürettiği bu makineyi kullandık, 3 boyutlu yazıcıyı kullandık. Bu işte metal için kullanılıyor. Ama elimizdeki done yanlışlıkla içeride bir bubble oluştu. Tak kırıldı.
Evet.
Yani bu resmiyete dökülmüş bir şey yani. Kaynakta mesela yüzyıllardır kaynak yapıyorlar. Amerika Liberty 2'ye böldü. Çatladı denizin ortasında. Bir şeyler yapıldı.
Evet.
Bu çalışmalar var mı? Yani garanti edilebilen, sertifikalandırılmış 3 megapaskalda kırılır. Bu makine 3 kalitede mal basıyor şeklinde bir şey var mı?
Şimdi gemiler bir şey, şimdi çoğu şeyleri dediniz yani şimdi uçaklarda her şey böyle daha zor certifying oluyor. Tabii uçağın düşmesini istemiyoruz. Eğer şimdi bir demirden bir parça uçağa koymak istiyorsak şu anda her parçayı test yapmamız gerekiyor önceden. Eskiden her birinci parçayı alıyordunuz, her birinci parçayı bir test yapıyordunuz. Bakıyordunuz her şey tamam mı daha. Şimdiki dönemde her şeyi %100 test yapıyorsunuz. Yani komple testiniz. Sadece buraya güç verip bakmıyorsunuz tutuyor mu tutmuyor mu. CT scan yapıyorsunuz. Yani içine bakıyorsunuz. Delik falan var mı içinde, bubble falan var mı içinde. Şimdi bunu üretiyorsunuz 120 euroya. Üstüne bir daha 600-700 euro katıyorsunuz test yapmak için. Onun için bu şeyler şu anda çok pahalı oluyor. Ama makineler ilerleştiriyor. Hani kaynak yapıyorsunuz yıllardan beri. Onun için çok iyi biliyorsunuz ki bunu böyle yaparsam 100 yıl tutar. Bunlar yeni şeyler. Yeni yapıldığı için de çok test falan yapmamız gerek. Bir yönde materyaller yani alüminyum kualifiyen olması gerek. Öbür yönde prosesin kendisi. Çünkü aynı makineyi alıp da peş peşe aynı parçayı yaparsanız 3 tane çeşitli parça alıyorsunuz. Yani hepsi aynı olmuyor bunların. Ama o yolda çok yapılıyor. Çünkü Airbus çok istiyor olması. Çünkü her seferinde 700-800 euro ödemek istemiyorlar bir parçaya. 120 euro ödemek istiyorlar. Ondan daha az ödemek istiyorlar. Şeyler çabuk olması gerek. Onun için yani her yönde oraya development yapılıyor şimdi şu anda. Garantisi şimdi şöyle. Eğer uçakta uçacaksa bu parça Form A paper lazım. Bu Form A paper diyor ki sana eğer bunu komple test yaparsan her şeyi tutarsa ondan sonra içinde bubble falan yoksa kullanabilirsin. Pahalı işte çünkü. Ama o zaman garantisi var o anda. Tabii ama her zaman da o şimdi başka bir şey. Bunu şimdi baskı yaparsanız yanına bir tane bir parçayı baskı yapıyorsunuz. Bu parça arşive koyuluyor. Eğer 20 sene sonra burada bir şey olursa o arşive bakıyorlar. O parçada da arıza var mıydı yok muydu? Ona yani garanti olarak kalıyor. Bu şeyi pahalı yapıyor. Şimdi bazı makine üretenler şey yapıyor. Layer by layer fotoğraflarını çekiyor. Şimdi fotoğraflarını çekiyor, onu fotoğraflarda görüyorlar sonradan. İçine delik var, oluşturmuş oldu mu olmadı mı. Ama şimdi buna fotoğraf çekerseniz aşağı yukarı 1 terabayt data lazım size. Bu sadece bir parça. Bir parça yaparsanız 1000 terabayt lazım. Bunların hepsi bir yere kayıt olması gerek. Yani şu anda çok sorular var o yönde. Plastik daha kolay oluyor çünkü HP'nin yeni makineleri var. Bayağı reliable parts yapıyorlar.
Sunumunuz için teşekkür ediyorum ilk başta. Ben imalat bölümünde çalışıyorum. Hı. Şimdi bu malzeme özelliklerine giriyoruz dediniz analiz yaparken. Benim şöyle bir sorum var. Eğer subtractive yani çıkartarak işlem yapıyor olsaydı talaşlı imalat gibi bütün malzeme özellikleri homojen oluyor doğal olarak. Biz de buraya girerken malzeme özelliklerini homojen gibi giriyoruz. Ama öğrencimiz güzel bir soru sordu. Evet. Eğer siz disk manufacturing yaparsanız kesit değiştikçe işte soğuma hızları değiştikçe malzeme özellikleri değişiyor. Bu programda bizim malzeme özelliklerini değişken şekilde girmemizin bir yolu var mı? Ya da yoksa nasıl yapabiliyoruz yani böyle bir şeyi nasıl düşünebiliriz? İkinci sorum da şu. Burada mesela biz optimizasyon derken siz bir herhalde arka planda son dönem analizi var. Bu analize göre belli gerilimlerin üzerinde kalan bölgeleri doldurma şeklinde yeni bir geometri oluşturuyor. Ama bu optimizasyon sadece malzeme azaltmak açısından değil de mesela süreyi azaltmak da olabilir. Bir de bu bizim malzemenin mesela FDM'de nasıl şekli yönlendireceğimiz, yani yatay mı, hangi yönde yönlendireceğimiz önemli
Evet.
oluyor. Bu tip de bir optimizasyon olabilir. Bunlarla ilgili bilgi veriyor mu? Bunları merak ettim.
Bunlar yapılacak şeyler. Also, ilk programlar başlıyor yavaş yavaş. Optimizasyonu yaparken diyorsun, sonra bunu böyle mi baskı yapacaksın, böyle mi baskı yapacaksın, böyle mi baskı yapacaksın. Onları kayıt ediyor. Ondan sonra bu optimizasyonu öyle yapıyor ki support structure'ları azaltıyorsun. Çünkü belki düşünebilirsiniz, yani havaya bir şey baskı yapamıyorsunuz, onu aşağı düşer. Demek altına support structures lazım. Bu support structure'lar sonradan iş yapıyor size. Çünkü sonradan çıkartmanız gerek bunları buradan. Hele alüminyum kolay, alüminyum elden çıkartabiliyorsunuz bazı yerde ama titanyum yaparsanız çok zor oluyor bu şeyleri çıkartmak. Yavaş yavaş o yola da gidiyorlar. Sonra yavaş yavaş şey de oluyor, heat treatment diyorlar ona. Yani baskı yaparken ısıtıyorsunuz bu parçaları. Sonradan parçalar çekiliyor gene içeri. Bunlarla simülasyon yapılıyor, analiz yapılıyor. Program sana direkt diyor ki şu tarafı azıcık daha ince yap. Çünkü yoksa o tarafı kalkar, yani olmaz o yer. Onlar da yapılıyor ama her şeyler çok yeni diye zor oluyor. Materyal döneminde şimdi X ve Y direction'da Young's modulün Türkçesini bilmiyorum. Young's modul ya ne? Elastiklik modulu. Yani X'den Y direction'da onu neredeyse iyi ama Z direction'da kötü oluyor. Onu da yapmaya çalışıyor. Çünkü şimdi ben bunu baskıya 3 tane baskı firmaya verirsem bunların hepsi bunu başka türlü yapacak. Sonunda 3 tane çeşitli parça gelecek. Her tarafa da başka türlü elastik modülü olacak. Onun için biz hep en düşük modülden hesap ediyoruz. Ama eğer tamamen biliyorsanız hangi taraf girecek diye programa diyebilirsiniz. Z direction'ı elastik modül böyle, X direction böyle, Y direction böyle diyebiliyorsunuz. Ya.
Şöyle, biraz yüksek söyleyeyim. Yani, Fusion 360 özelinde konuşacak olursak, yani sonda elemanlar analizi üzerinden parça eksikliği, optimizasyon o anlama geliyor burada, dar anlamda bakacak olursak. Ama sizin söylediğiniz baskı optimizasyonları için yine bütün eğitim camiasının ücretsiz erişebildiği network gibi yazılımlar var. Otodesk'in bünyesinde. Emrecan hocamız da yani kullandı, kendisi de o konuda bilgi sahibi. Yani hem simülasyon hem de işte destek parçalarının optimizasyonu gibi süreçleri onunla da yapabiliyorsunuz. Onlar da sizin doğrudan indirip kullanabileceğiniz yazılımlar.
Sunumunuz için teşekkürler. Benim şu konuda bir sorum olacaktı. Parçaların uçaklarda kullanıldığını ya da kullanılabileceğini söylediniz. Ya uçaklarda çok fazla sıcaklık değişimi oluyor. Yani uçakların çıktığı yükseklik ve tekrar indiği yükseklik konusunda çok fazla sıcaklık değişimi oluyor. Bunların simülasyonları yapılırken sıcaklık değişimleri vesaire de hesaba katılıyor mu? Birinci sorum. İkinci sorum da biraz önce yaptığınız simülasyonlarda ya görmedim ya dikkat etmedim. Bir çalışma sıcaklığı atamadınız. Hani program kaynaklı bir özellik mi yoksa hani sadece mekanik simülasyonları mı yapıyorsunuz burada?
Şimdi gösterdiğim sadece mekanik simülasyon ama eğer uçak için bir şey hesaplıyorsak çeşitli yani minus 50 degree zum 100 degree onları hesaplıyoruz tabii ki. Evet. Bunlarla yapabiliyorsunuz. İsterseniz göstereyim ki burada çok bir daha. Buraya simülasyona gittiniz mi? Bak burada burada bir defa var. Sıcaklık üzerine stres hesaplayabiliyorsunuz. Bir de sıcaklık hesaplayabiliyorsunuz. Yani ne kadar sıcaklık kaçıyor o sıcaklık altında ne kadar stres oluşuyor. Şimdi eninde sonunda topoloji optimizasyonu yaparken bir gün bunların hepsi bir araya gelecek. Hepsi bir araya yapılması gerek çünkü 3D print için önemli o yani nerede ne kadar sıcaklık var. Şimdiki dönemde alüminyum veya titanyum baskı yaparsanız hepsi sonradan hep prosese giriyor. 900 derecede bir de 20 bar basınç içerine birkaç saat içeride kalıyor ki delikler kapansın diye bir de elastik modülü bulsun diye.
Yükleme koşulları sadece statik mi oluyor? Dinamik olarak yükleme koşullarına da maruz bırakabiliyor muyuz?
Onu belki siz daha iyi anlatabilirsiniz.
Ben konuya girmeyeyim.
Okay. Dinamik şu anda o kadar çok yapılmıyor anda. O şeyleri çoğu zaman başka programlar kullanıyoruz. Bizim customer'lara bağlı. Yani herkes başka bir şey istiyor bizden. Yani başka programlar kullanmamız mecburiyetindeyiz o zaman. Ya. Şurada önde var bir soru.
Kısa bir sorum daha olacak. Firmanızda prototip üretiyorsunuz anladığım kadarıyla,
Hı-hı.
değil mi? Bu prototipleri ürettiniz, çok sayıda ürettiniz. Bunların geri dönüşümüyle ilgili bir şey yapıyor musunuz? Ya da bu titanyum tozlardan nerede üretiliyor? Sizin üretilen parçayı nasıl geri dönüşüme gönderiyorsunuz firmanızda? Bunu merak ettim. Titanyum parçaları.
Şimdi titanyumla biz sadece plastik üretiyoruz. Plastik üretiyoruz ve satmıyoruz bunları. Bunlar sadece bizim kendimiz için prototip olarak yapıyoruz. Bizim iş yerine çalışan kişiler öğrensin diye yapıyoruz. Eğer bir şey satılacaksa bizim customer'da bizim cooperation partnerlarımız var. Onlar o satışı yapıyor o zaman. Onların elinde kalıyor onlar. Çünkü biz 70'li senelerin beri sadece hesap falan yapıyoruz, construction yapıyoruz. O tarafa hiç gitmek istemedik. Onun için o partnerlerimiz var, onlarla beraber yapıyoruz o işi. Yani tam diyemeyeceğim size o alanda.
Benim sorum şeyle alakalıdır. Ben imar mühendisliği okuyorum. Hani biz katmanlı imaratta bir parça üretirken girmek istediğimiz parametreler neler oluyor? Hani mesela bir siyasi talaşlı imarat yaparken ilerleme hız tarzında parametreler giriyoruz. Burada girdiğimiz parametreler neler? Hani toz seçimi nasıl oluyor? Onlar hakkında ben merak ediyorum.
İşte orada yani tabii materyalden bağlı parametreler var ama bizim için enteresan olan şeyler biz ona design guideline diyoruz. Çünkü bazı şeyleri yani her şeyi de yapamıyorsunuz. Nasıl diyeyim bir top üretecekseniz içi dolu olmayacak. Yapamıyorsunuz. Çünkü içindeki o powder içinde kalıyor o anda. Bir yerden çıkarmanız gerek. Onun için şimdi yavaş yavaş design guidelines'lar geliyor. Onlar sana diyor ki şu parametreleri kullanabilirsin. Ya da titanium baskı yaparsanız orada yazıyor ki bir 45 derecenin aşağı olmayacak. Yani böyle bir şey baskı yaparsanız kolay. Böyle bir şey de kolay ama böyle bir şey yaparsanız buradaki şeyler düşebilir o anda. Onun için diyor ki sana 45 dereceden aşağı gitmeyeceksin. Yani eğer gidersen de bir support structure lazım sana diye. Öyle design guidelines geliyor. Doğru anladın mı? Ya? Bu parametreleri.
Ben şeyden soracaktım.
Sorun.
Ben TEİ'deydim. Orada metal olarak imalat yapıyorlardı. Mesela imalat %90'a geldi. Bir katman arasında hata olduğu zaman imalat komple duruyordu. Baştan o parçayı üretmek istiyorsak sıfırdan başlıyordu.
Evet.
Bunun sebebi ne? Onu biliyor musunuz?
Bilmiyorum.
Yani imalat sırasında lazer ısıl işlem uyguladığı için orada distortion'lara sebep veriyor. Orada da katmana geçerken üstünden 30 mikron üzerinden blade geçiyor. O blade oraya çarptığı anda imalat durduruyor. Oradan devam etme şansı da var ama işte iyi hesap yapmadan dizayn edersiniz. Bazen geri dönüş olmuyor.
Zaten onun için de biz bir şey dizayn yaptık mı? Hep dikkat ediyoruz ki fazla materyal bir yerde olmasın. Eğer fazla laser giderse o yerden çok sıcak oluyor o tarafta. O sıcak olan yerde tabii o anda da kopabiliyor. Ondan sonra blade'lere çarpıyor.
Ya da support'u düzgün koymak.
Support onlardan geliyor. Bazen de sadece bir parça makinede değil. Bazen o makinede 6, 7, 8, 10 tane parça var. Bir tanesi kırıldı mı öbürleri de duruyor o anda. Yani hepsini komple yeni yapmanız gerek. Titanyum pahalı yani 1 kilosu 450 euro. Büyük makineyi doldurdunuz mu aşağı yukarı 1000, 2000, 3000 euro powder var onun içinde. O anda durdu mu onun için o işi oraya biz çok dikkat ediyoruz ki öyle bir şey olmasın diye.
CT scan'de parçanın ne kadar kalın bir parçayı tarama yapabiliyorlar?
Bilmiyorum. Biz kendimiz...
Bir limiti var galiba.
Olabilir ama CT scan gerçi yani onlar senelerden beri yapıyorlar. Yani bayağı iyi yapıyorlar şey. Also biz bazen yapıyoruz. CT scan yapıyoruz. O CT scan yani Trenweiler var. Trenweiler bazıları 40, 50, 60 sene yaşında. o parçalar bazen bulunmuyor da. Ondan sonra bazen drawingleri de bile yok. O zaman parça geliyor, biz masaya koyuyorlar. Reverse engineering yapmamız gerek. Bazı şeylerin içine bakamıyoruz. Onun için CT scan yapıyoruz. O CT scan'den parçayı yeniden üretiyoruz. Reverse engineering diyoruz işte buna. Bayağı iyi yani, beni sanmazdım yani. Ama tam olarak bir net sayı veremeyeceğim size.
Elinizdeki parça hangi sistemde üretildi acaba?
Bu şey EOS, Almanya'da bir company.
Sistem olarak biojetik mi yoksa?
SLM, Selective Laser Melting.
SLM'de peki support gerekiyor mu?
Buna support vardı, evet. Bunun şu alt, hani böyle baskı yapıldı. Şu altta support vardı. Bir de şuralar az bir şey vardı.
Tozun üzerine yapmıyor muydu?
Şimdi bu toz o kadar ince ki.
Kaldıramıyor.
Evet, kaldıramıyor. Yani o tozun üstüne bir şey yaparsanız o tozun içine iniyor. Zaten bu tozu bir küçük bardağın içine koyarsanız, azıcık çalkalarsanız aynı su gibi. Yani o kadar ince bir toz. Zaten onun için o şeyler pahalı.
Mesela de şey oluyor.
Evet.
Peki şimdi biz bir makine ısıtmamız gerekiyor. Mesela SLM'de. Oraya koyduğumuz tanecikler yaklaşık herhalde 30 mikron civarında tanecik boyutu. Bu tanecik boyutu ısıttığımız zaman, genleştiği zaman geri dönüşme oluyor mu? Yani burada kullanmadığımız tozları tekrar kullanma imkanımız oluyor mu?
Toza bağlı. Bazı makineler oluyor, bazıları olmuyor. Şimdi şeye bağlı. Airbus diyor ki bunları sakın bir daha kullanmayın. Testler ama gösterdi ki bazı şeyler, bazı tozlar birkaç defa kullandıktan sonra daha iyi oluyorlar. Çünkü nasıl diyeyim, filtre oluyorlar. Yani onun için yani bir tuhaf ama Airbus diyor ki mecbur yeni olması gerek, çünkü o zaman diyebiliriz ki doğru. Bazı işte %30, %40'ını değiştiriyor sadece. HP printer'e bakarsan o %100'ünü kullanıyor ama plastik o tabii. Çeşitli yani şeye bağlı, kasımaya bağlı. Ya. Başka soru? Ya. O zaman bu kadar. Çok teşekkür ederim. Eğer birisinin sorusu varsa ben buradayım. Eğer birisi bachelor ya master tezisi için bir fikir almak istiyorsa, almaya gelmek istiyorsa onun için de yani sorabilirsiniz isterseniz. Ya, bu kadar.
Arkadaşlar son bir şey söyleyeyim. Yani duyuru yapmıştık, onun sözümüzün arkasında durmak için katılım sertifikası verebiliriz. Eğer isminizi kaydettirirseniz sizin için bir sertifika hazırlayıp göndereceğiz ama isminizi almamız lazım bunun için. İsterseniz nasıl yapalım onu? Bir kağıt hazırlayalım buraya. Sadece isteyenler kalabilir yani onun dışında.